Welcome back to the Art of Math. In today's video we're going to go over fractal substitution application and talk about Markov chains. Now this is going to be the last video in this huge algebra chapter before we go into the geometry section. So alright, let's get started. So in the previous video we talked about this super awesome fractal substitution, and here's going to be more of a real life problem. I mean, this is not what you're going to encounter every day, but this will be in a lot of, let's say, engineering or technical disciplines. So here's a problem. Let's say there's three states. You can be in position A, position B, or position C. So you could think of this as like abstract states or actual geographic locations or towns or whatever. So if you're in this position, then all these little numbers I've written down, these are all probabilities. Now we're going to do probability in depth much later, but for now this will be just basic probability. So if you're in A, there's some probability. This 0.1 means there's a 0.1 chance or 10% chance that you go to state L, position L. So L means you lose. W means you win. So we want to get to W, and we're going to assume the question we're going to try to answer is, if you start in A and the numbers basically tell you how the game works, what's the probability that you're going to win? So this bar just means given or conditioned on. We'll talk about that much later. But it just means assuming you start in A, what's the probability you win? So that's what we're going to go over. So if you start in A, here's how it works. There's a 10% chance you automatically lose. There's a 50% chance you just do a loop and end up back in A. So like nothing happens. You just you just wait basically. There's a 40% chance you move on to position B. Once you're in B, there's a 20% chance you just loop around B. There's a 10% chance you go back to A. There's a 70% chance you move on to C. Now, once you're in C, 10% chance you go back to B. 10% chance you win. And from C, there's an 80% chance you return to A. So basically, this looks like this really complicated web of numbers. And so if I said, what's the probability if you start here that you're going to win? Well, it's not 90% because there's a 10% chance you lose, but the 90% chance just means you keep on playing, but that doesn't necessarily mean you win. So it's not obvious what that probability would be. So in order to approach this problem, we're going to use substitution. So let's think about it this way. If you're in A, there is a 10% chance of losing, so we could represent losing by 0 and winning by 1. So that's what this will be right here. Now I've put, now this box, this is really the key to this whole problem. So the 0 just means, I crossed this out because 0.1 times 0 doesn't contribute anything, so we can just erase it. So if you're in position A, also let's just define what all this stuff means. So we're going to let A, this is actually poor notation. I should technically let it be P sub A, like the probability of A, but I don't want to have a ton of letters everywhere, so in the interest of simplicity, I've just written these letters. So we're going to let A be the probability of winning starting in state A, and so on and so forth for B and C. So that's the probability. B would represent the probability of winning if you start in B, and so forth. All right. So now let's go to this box. This is the heart of the problem. So if you're in A, there's a 0.5 chance that you just return to A. There's a 0.1 chance you lose, and there's a 0.4 chance you move on to B. Now this may look straightforward, but really this is super duper clever, and this is fractal substitution, because this is not really an A. What you're doing is there's a 0.5 chance of repeating the game. So I could really expand this inner A. So think back to that square root of 1 plus the square root of 1, like all those nested radicals, or 1 over 1 plus 1 over 1, all that repeated stuff. This second A is really 0.5 times another, like it's a whole nested thing. So instead of this inner A, I could replace it with this outer definition. So I don't want to have this infinitely nested thing, so I've just replaced that whole crazy thing with just A. So now it looks really nice, right? So the chance of winning is 0.5, the chance of winning plus 0.4 of the chance of winning from state B. So we're going to do this from every state. So the chance of winning from B, and we're just going to use these numbers. So 0.2 of going back to B, so like you're restarting the game, and the odds of winning from B is always just B, so these B's are the same. 0.1 chance of going back to A, so 10% of going to A, 70% chance of moving on to C. Then same thing with C, we just put on all the right numbers and we have this system of 3 equations. Now I want to stress, at this point we've talked about systems of equations and solving it. The application here is not in solving this. It's the insight that we could set it up this way. It may not be obvious. I really want to stress that you could just represent this A in terms of that A. So, and in terms of those other letters, you might think that, wait, the initial probability is not tied to that probability after 2 turns, but the insight is it is. Just like in the original fractal substitution, we replaced a part of the problem with the whole problem. So we had this nested effect and we could solve for what we set it equal to. So maybe some of you got this really quickly, but I found this pretty profound that we could just set it up this way, where this A encapsulates 0.5 times 0.5, like infinitely go, because you can repeat, you can do these loops in infinite amount of times. All right. So, and then we're just going to solve this. So I don't like all these decimals. So this is just mechanics and systems of equations. I see all these decimals, so let's multiply everything by 10. That's how I got all these equations. Just multiply through everything left and right by 10. Then using the first equation, it just so happens there's no letter C in here, so we can get a nice substitution for A in terms of B. So we're going to get A is 4B over 5. Again, don't focus on this so much. This is just the details of mechanics. Then we can plug this into equations 2 and 3 to get these. So now we've eliminated the A. It's some messiness. We simplify, so we just have B's and C's. And then we're going to get B in terms of C. So, you could follow the work I have here. I'm not going to read all of it. I think it's a waste of time. So B is 35C over 36. You can plug that into this equation. You're going to get really ugly numbers. I've multiplied through everything by 36 over here in case you're wondering why, to knock out that 36. And then you just move all the C's to one side and then divide through. So if you do this properly, 2 systems of equations with 2 unknowns, you should get C's about 0.356. So if you start at C, you have about 35.6% chance of winning. B, we're going to use that substitution, so now B's 34.7%, and A, the original question, is about 27.7, so let's just say about 28% chance. So the answer to the original question is we have a 28% chance of winning if we start at A. Now, I just want a quick note. I want to point out that careful with the rounding. So notice I put all these estimated symbols. So once we estimate C, I didn't plug this value to get that B. I plugged in the full calculator value to get that B. Otherwise, if you start rounding on top of rounding, you'll have more, and the errors will grow. So be careful. Don't plug in the rounded versions. Plug in the whole thing with like 8 or 10 digits, whatever. So same thing. I didn't use this value to get A. I actually used more digits to get A. I'm just showing you brief versions. All right. So I'll leave it at that. Hopefully you found this cool. So you could simulate any sort of game you want. There could be more states. Obviously, if you have more states, it'll just be more equations, more messy. You might need a computer program or calculator to solve it. All right, so I'll leave it at that. I want to wrap up with a terrible joke. Terrible joke, indeed. So let's see what kind of terrible joke I have. What did the tree say to the math teacher? Gee, I'm a tree. So, and with that, we are going to begin geometry in the next video. So stay tuned for that. See you guys there.